If you've taken Algebra 2, you've likely been introduced to imaginary numbers. Really? I mean, come on, Descartes. You called them imaginary numbers. People who hate math already have plenty of reason to argue that mathematics is pointless, and you dangle a necessary part of mathematics in front of the masses and have the gall to call them imaginary? Modern education remaining surprisingly traditional aside, let's talk about imaginary numbers. I think I've already made it clear by now, but you're probably still wondering to this day why your high school thought it was important to teach you how to work with imaginary numbers. See, just saying it out loud makes it sound ridiculous. But the truth is, there's actually a great deal of importance to learning about imaginary numbers. The problem is that its use cases are limited to engineering, physics, philosophy, and mathematics itself, which is only a small subset of the occupations in which people who have ever attended high school will actually participate. The importance of imaginary numbers is less about how we use them and more about the potential doors that they open. So let me give you an example. Let's say you lived in this reality, the one that we call our own, right? But then let's say there's a door that exists somewhere in the world, only one door, that allows you to enter a parallel reality. Mostly everything is exactly the same in this parallel reality, but there's a few major differences. Imagine things like world leaders being different. The sky is just a little bit more green. The food tastes just a little bit off. Imaginary numbers are proof of the idea that that door can exist between the precipice of reality and fiction. Okay, but maybe I'm getting a little bit ahead of myself. What is the actual math behind an imaginary number? Well, let's talk about squares and square roots. Squaring a number means to multiply it by itself. For example, 3 squared is 9, because 3 times 3. However, negative 3, that whole value squared, is also 9, because it's negative 3 times negative 3, and 2 negative numbers is positive. So there exist 2 different values which, when squared, yield the same result. If we take the square root of a number, say 9, that means what number, when multiplied by itself, is equal to 9? Well, sure, 3 is one such number, but negative 3 is another one. But that's one value that, when square rooted, yields 2 results. That's not normal. In fact, if you were to square any number, you always get a non-negative result. So that means that if you take the square root of a positive number, you actually get 2 results. But then what about taking the square root of a negative number? Wait, let's think about parity for a moment here. We need a number that, when multiplied by itself, is negative. Well, there are 3 possibilities for that number. 1, the number is positive, and a positive times a positive is positive. 2, the number is negative, and a negative times a negative is positive. 3, the number is 0, and 0 times 0 is 0. So it looks like all these results are non-negative. So is this it? Does this mean that we cannot take the square root of a negative number? Well, yes, using a more traditional approach to math. But what if we could? What if, by some miracle, we could take the square root of a negative number? What if we could find that one and only door to a parallel universe? What if we used imaginary numbers? And thus, I is defined as the square root of negative 1, and imaginary numbers are suddenly possible. Okay, great. So we have the door to the parallel universe, but now that just means that we stay in this parallel universe for the rest of our lives, right? Here's the crazy part about the parallel universe. You can travel back to your original universe, but not the same way you entered. Let me give you an example. We just defined I as the square root of negative 1, but what if we squared I? Suddenly, I squared is equal to the square root of negative 1 squared, which is just equal to negative 1. Guess what kind of number negative 1 is? That's right, it's real. That means that not only is there a door to a parallel universe, but there's also a way to get back home. And that is the interesting part. That is the reason we study imaginary numbers. Therefore, it stands to reason that events in reality affect events in the fictional reality, and even more importantly, events in the fictional reality affect events in the actual reality. This is a philosophical form of evidence towards the idea that math with imaginary numbers can yield meaningful results with real numbers. And that's more or less the point of this video. If it can be shown that there is a gateway from real to imaginary and vice versa, then the math that we can only do using imaginary numbers translates into meaningful conclusions in real life. The most useful equation that comes to mind when using imaginary numbers is Euler's identity, which states that e to the power of I times pi plus 1 is equal to 0, or that e to the power of I times pi is equal to negative 1, which is a combination of real and imaginary numbers that are always true. Like I said before, the use cases for imaginary numbers are admittedly very small, but they exist. To be completely honest, I believe that school teaching imaginary numbers is secretly a form of academic indulgence, the same type of gluttony you feel when you've taken your final exam for a course and have about a week of time to spend on watching movies in class and hanging out with your school friends before the summer vacation starts. The idea that you could step into another reality and at some point find your way back home to what you would consider to be your true reality, and even encouraging that delusion in an academic environment, gives me hope that education can not only be made fun, but be standardized as fun. Thank you all for watching, and have a great day.